Hi everyone. So today we'll start talking about Taylor series. And polynomial approximation. Just in case you haven't heard, yeah, so we have, we extended, so you can submit homework 9 by August 8th. Yeah, midterm 2 is this August 1st. What else? I think that's it. Oh yeah, and we have nighttime office hours. So on Friday, this Friday, all Fridays, I finally got enough people to attend. So 3 to 4 and 9 to 10. Yeah, they're in the announcement. I think it was like 3 to, I think 3 to 7, and then 9 to 1. Something like that. Yeah, I think that was it. Oh yeah, and please tell me for August 19, please tell me if you have any other tests. So I know many of you have it with Justin Co. So APM 346, but any other ones? Because I want to, because currently it's at 7 in the morning and 7 at night. But I think this is too early for you guys. So I wanna see if there's any conflict. So maybe I can put it like 12, like 12 to 4, and 9 to 1. So, but I need to know if you have conflicts. So please tell me. Let's start with the Taylor series. Yeah, I know I didn't quite finish AA, but we went through the main argument, which was the diagonalization question. Yeah, exactly. So we didn't quite finish math 334. What do you mean for math 334? Matthias, I don't know what you mean. Okay, sure. Yeah, we didn't finish. I mean, the last step in AA, it wasn't hard. So, and it's in the book. I just wanted to go through the diagonalization. That was really the hard step. But the last 3 lines in AA are straightforward. Um, but of course, we can talk about them as. So if you stay after class, I can go over it with you, and we can talk about it. Right, let's start. So I know many of you have seen Taylor series, so I'm not gonna do too much of the computation. I'm mostly gonna focus on the theory. So the Taylor polynomial. So for f, C n differentiable, So n derivatives, n continuous derivatives. Pn of f of x. Okay, right, and then one more thing, and fixed a in R. The Taylor polynomial at does he write that? He doesn't write it. Well, I think this is better notation. So Pn of A is the following polynomial. So f of A, it's a constant, first derivative at A, and then x minus A, and then double derivative at A, x minus A squared, and you keep going till you get the nth derivative evaluated at A, x minus A to the n. So this this polynomial is called the Taylor polynomial. Okay. Now, why is this interesting? Well, let's just do a simple case. So for n equal to 1, you have Pn of A. Let's put A equals 0. So f of x is equal to f of 0 plus f prime at 0 x. Now, if you go and you draw this, and let's do something like x squared. Then this is the approximation. So a linear approximation. But our graph is not linear. Our graph is not linear. So we need to add more derivatives, to add more terms, more derivative terms. To get a better approximation. So this is for f equal to x squared. So I claim that you only need one more in this example. So indeed, I mean, P2, 0, f of x, you have f of 0, f prime at 0, x, and f double prime 0, x squared. And let's see. So for f equal to x squared, you get, what do you get? You get 0 squared, you get 2 times 0 times x, and then you get 2 times x squared. Yeah, there's over 2. Yeah, I forgot to add this. I should have added this. So this is 2 squared and then n factorial. So yeah, you divide by 2, and so you get x squared. So P20 f of x is equal to, let me add it, let me do x squared. P20 of x squared is equal to x squared. Isn't that cool? So we captured, or the nonlinearity. Okay, but for f equal to the exponential, no amount of terms of finitely many terms will give Pn of e to the x equal e to the x. So this is never true. And we'll talk about it more. I see a question. Yes. Isn't it a compact set? What? Taylor series is global. So for exponential, you have Taylor series everywhere. So I'm not sure what the question is. Okay. So let's see. So for example, if you recall, e to the x, we found its Taylor series. It was 1 over k factorial e to the x. This is for all x in R. So I want to talk about, the exponential. Let me go a little bit deeper on this. So example. Let's work with the exponential. For f equal to the exponential. Let's find its Taylor series. I say recall, but we didn't actually prove it. So let's find Pn of Vx. Well, what do we have? We have Pn at 0. So when we don't write anything, we mean at 0. So we have e at 0, and then derivative of e to the x at 0, and then the nth derivative at 0, x to the n. And so you know that e prime of x is e to the x, so you get 1 x x to the n factorial. Okay, so that's how we find the Taylor series. I had a remark. So for n equal to 10, you already get a very good approximation. So e to the 1, p to the 10 of e to the x at 1. So you get k0 to 10, 1 over k factorial. So I did this in Wolfram alpha. You get, I just want to write that you get a ratio, which I find it interesting. Not surprising, of course, but interesting. And then if you do it in Wolfram alpha, you get a very good approximation to let me just write it like this, to e to the 1. So I just want to make the remark that so going back to the construction of the reals, Taylor polynomials are good candidates are Cauchy sequences rational Cauchy sequences. For irrational numbers, approximating irrationals. Okay. This guy is irrational. This guy is rational. So, yeah, so Taylor polynomials give approximation to irrational numbers, and really that's what happens. That's how we encode irrationals in computers. All right. Okay, what's next? Yeah, but of course, the big question is how good is the approximation? So that's the theorem. Right. So suppose f is n continuously differentiable, then what do we have? We have f of x is equal to this approximation at around a plus constant that depends on x, and then x minus a to the n plus 1. And anyhow, so this guy is not 0. So let's prove this. This is the easy version. We'll do a harder one where we actually find what this constant is. But if you want some constant, then it's fine for some c and x. So we just do L'Hopital. I like this proof because it's a one-liner and it gives you the idea of Taylor series. So we have, what is it? F a plus h what do I want? I see. Let me say exactly what we're doing. So take x to be a plus h. Want to show that that f of a plus h minus the approximation minus the approximation divided by h to the n plus 1. We want to show, what is it? I think I made a little typo. Yes, I want to say n. We want to show that this limit exists. Okay, and that would what we would call a Cn of x. Okay, so we have f of a plus h minus this approximation. Right. So what do I want to say? Yeah, so this stays as it is. And yeah, here we have f of a plus, what is it? f prime of a h fn a h to the n. Okay. All right. Now, unfortunately, we have to do some work here. We have to split it. Right. So we see that that as h goes to 0, top guy goes to 0, and bottom guy goes to 0. Top guy goes to 0 because f of a plus h minus f of a goes to 0, and all these guys are functions of h, so they all go to 0 too. All right, so we have 0 over 0, and we can do L'Hopital. Okay, so by L'Hopital, what do we get? First guy becomes prime, the constant disappears, and you get f prime of a, and then what is it? F double prime of a h, so it was 2h over 2, then triple a 3h squared over 3 factorial, so on. And underneath we get n times h to the n minus 1. Let me see if there's questions. Okay. Again, this is 0 over 0, as you can check. Why is it? Okay, good. Because I keep forgetting my my factorials. So yeah, so let's see. So where did this come from? This is the derivative. Let me do it on the side. So we took ddh of Pn of a plus h, and so ddh, and one of these terms, so you have f of a, f prime of a h, and then one of them is h squared over 2. Derivative is linear, so you get 0, f prime of a, and then f prime 2h2. Okay, Bin Yao. So I know they don't do this in the book, but it's a nice clean proof. It gives you why we choose the coefficients. So we chose 2 factorial to get cancellations. All right, anyhow, so repeatedly doing L'Hopital. What do we get? We get, so we do it n times, so you get n minus 1, 1, and then you get, let me see, it was n minus 1. I need one more. Let's see. So h, and then is it n minus 1? N minus 1 to the a plus h minus f of n minus 1 to the a. All right. This is a bit messy, so let me write more clearly. So we got the limit as h goes to 0 of fn minus 1a plus h minus f of n minus 1a and factorial h. All right, good. but this is just the limit definition of derivative. So n factorial comes out, and we get the n derivative at a. So this is the constant. So indeed, actually, let me make a correction. I wrote x, I should have written a. And so Cn of a is f of na over n factorial. Okay. Question. Shouldn't f prime has a coefficient a half? Shouldn't f prime have a coefficient a half? No. You can see here it's divided by 1. No. No, I mean the 2 shows up for the second derivative, so they always match, right? So we always have, how do you say it? We have f of n minus 1 to the a. Actually, that's not a good place to write it. Let me write it here. So we're taking, so what is this polynomial? It goes all the way to n minus 1, a, and then n factorial. H to the n. So they always, no, n minus 1. They always match, derivative and denominator. All right, anyhow, so that's the proof for that. So anyhow, that's it. But we can find explicit error. So this is the one from the book. So Taylor's theorem. All right. So let me see. Where am I? Here. Let me not. Where am I? Here. Good. Let me just say this. All right. Let's move on. So, where am I? Here. Yeah, but suppose that f is Cn plus 1 differentiable, then what is it? Then you can write the following. F of x is equal to Pn of f plus, in the book they call it Rn of x. But let me write what it is. So you have the n plus 1 derivative, and I will say what this constant c is, times x minus a to the n plus 1. So we're seeing is inside x a x big A. So this is the C from mean value theorem. So we will apply, in a way, a mean value theorem, which is also called Rawls. Yeah, we'll use Rolle's theorem. All right, let's go into the proof. All right. Okay, so this is not in your book. I'm using a different proof, just so that you have multiple proofs of this fact. Okay. Fine. Either the following function, f of y is equal to fy. So we take the difference, Pn of fy minus some constant times y minus an plus 1. Okay. And want to show that k is what we said. I don't know why I'm calling it y. I can just write x. No, I need y. Now I remember this. And y is in this interval. Okay. So what's the deal? Yeah, we will apply Rolle's theorem. What's the logic? Rolle's theorem said that if there exists AB such that f of A is equal to 0, and same for f of B, then there exists C in their interval such that the derivative is 0. So the function does something like this at AB. You can find the place of zero slope. Okay. So that's Rolle's theorem. But in our case, what do we have? For y equal to a, we get f of a, and k times 0, because it's a minus a. Let me just write it. But again, all these things cancel out, and you're left with f of a minus f of a. So you get 0. Okay. You get 0. And the next one is we let x to be, we let y to be x, and choose k such that f of a, and choose k, how do you say it? X minus a. We get f of x minus f of x, Pn of f of x minus a to n plus 1. Again, by definition of k, we get 0. Okay. So by Rolle's theorem, there exists a C in, let's take X to be bigger than A. We'll just take this to make our life easy. Such that f prime of C is, and I need a label, so it was C1, is 0. Okay. All right. So we will repeat this n times. Repeat this. Yeah, n plus 1 times till x minus a n plus 1 disappears. Okay, so let's do them again. Since f prime of a is equal f of a minus f prime of a, f double prime of a, you know, a minus a, so on, and k, a minus a. We again get 0. And since f prime of C1 is 0, we get that there exists C2 in A C1, such that f double prime C2 is 0. Is that okay? One person. 2 person. I see 9 people. So either, okay. All right. At least I have 3 people watching. Okay, 4. All right. So repeat this. To get Cn plus 1 in ACN, such that f, what's my derivative? N plus 1. N plus 1, Cn plus 1 is 0, right? Yeah. So you get that, which is fine because f is in Cn plus 1. So we can take the next derivative. So, which is fine, let me say, which is okay. All right, but what is, but f of n plus 1 of y, I wrote it here, is f of n plus 1 y minus n plus 1 factorial k. All right, so we found our constant. So our constant is so 1 second, and then we have n plus 1, Cn plus 1 is 0. So by solving for k, we get what we wanted, which is what we got with L'Hopital. So there are many ways to do this. We're giving you multiple proofs. Okay, so let's do some examples. Get a feeling for this. Let's go back to the exponential. So by Taylor's theorem, we have the following. We have e to the x is equal to Pn of e to the x plus e to the x n plus 1 derivatives over n plus 1 factorial times x to the n plus 1. And that's at x equals 0. So let's open this up. You get 1 x squared over 2, x3 over 3 factorial, x to the n. How do you say it? N factorial, and then you get your error. So this is e to the c over n plus 1, and then x to the n plus 1. Okay. So you see, you get this extra guy here that you don't have here. So this is the error. So what do we mean by that? We mean that suppose you want to find how good the approximation is. So you have sup x in some compact interval, e to the x minus Pn e to the x. So how good is the approximation? So we have this. We just found what the error is. It's equality. So we get e to the c n plus 1 factorial x to the n plus 1. Okay. So we have all these errors, and also we know c is in close to 0 in x. Fine. So then you have the following bounds. You have, e to the a, n plus 1, and then a to the n plus 1. Okay. So how good is this? So how fast is the error? Well, recall by Stirling, you have n factorial grows like n to the n. So going back, we get e to the a, and a n plus 1, n to the n plus 1. So e to the a n, but a is constant. So this goes to 0. So going back to, I think it was Mateo's. So we get Pn of e to the x uniform for x in compact intervals. We get uniform convergence of the Taylor polynomial, but in compact subintervals. But of course, the series is defined everywhere for all x. But if you want uniform approximation, then you have to look at compact. So, let's see, whose question was that? Oh, it was Ajit, yeah. So yeah, hopefully that's clear now. So yeah, you need compact to get uniform convergence, but otherwise the series is defined everywhere. So yeah, that's for Ajit. He had a question for compact. All right, we have some time. I should do. What should I do? Yeah, so let's drive this point even more. Why do we have to be careful? So far everything looks good, but let's see when Taylor polynomials are not good approximations. And this will motivate the next theorem that we will do in this class called Weierstrass, where we come up with a better approximation. So we will do some examples of not good approximations, and then today and next week, Thursday, we'll give you a powerful theorem called Weierstrass. Okay. So this is also in the book, but it's a very good example. I wanted to do it. So this is called smooth but not analytic. We'll explain all these words. Okay. So let's first do the example, and you'll see. I'll explain what we mean. So let f of x equal 1 plus x squared. Now, this guy, as you can see, it has all its derivatives. Hence, we call it smooth. Right? So you can take any derivative you like, they're all defined. So, did I compute? Actually, it's a bit messy to find the derivatives, but you can see it by induction, that you have all the derivatives by induction. Okay, that's good. But its Taylor series is not defined everywhere, which is kind of surprising. So let's see why that is. Okay, so for x less than 1, we use geometric series. So we use geometric series. Yeah, let me finish this example and then we'll take a break. We have 1 plus x squared. You can write this as 1 minus x squared. So you get minus x squared to the k. Let's write this a bit more clean. So minus 1 to the k, x 2k. Right. Okay. Fine. But yeah, this series. So you have one. Sure. So you have this guy equal to that guy. And then, okay. But now suppose, so I'm doing a general proof to give you an idea how to disprove Taylor series approximation. Suppose you did have, fkx around 0, yeah. And then k factorial x to the k, right? Suppose you had this for all x in R. Okay. So step one, we have, by equating coefficients, we're using the fundamental theorem of algebra. We get fk0 k factorial x to the k. Well, let me write it differently. Yeah, okay. Anyways. We get 0 when k is odd. And otherwise, we get what we have on the left, x to k, right? So this is for x less than 1. Okay, fine. But the problem is, but summation of these guys blows up for x bigger than 1 or even equal. So summation of fk0 k factorial x to the k is only defined for x less than 1. Okay? So even Taylor series have radius of convergence. Which is not surprising, but we have to make it clear that they're not perfect approximations. Right? So e.g., if you want to find 1 plus 10 squared, you cannot use Taylor series. Which is, to be honest, surprising. Why not just take derivatives and then put x equal to 10, where it will blow up, so it will not work. But anyways, let's take our break, 10-minute break. All right, let's start. Yes. Okay. Right. All right. Yeah. Let's do another example. We talked about this a little bit. It's again a very commonly found function. So, let f be this arctan guy, arctan of x. Then we did this. So from previous class, what did we do? We had, arctan of x is the its antiderivative. Its derivative is 1 plus x squared. And so if you have x be less than 1, you have s is less than 1. So you can do geometric series as above. And we get the same issue because this is the exact same example, but integrated. So we get minus 1 to the k, 2k plus 1, and x to the 2k plus 1. This guy converges for x in what? In, let me see. Yeah, in both, minus 1 and 1. Fine. So the Taylor series, so fk at 0, k factorial is 0 when k is odd, when k is even. And, when it's odd, you get minus 1 to the k, 2k plus 1. Okay? So this is k odd. I mean, yeah, we wrote it. So these are the Taylor coefficients. If we ask you for, so these are the Taylor coefficients. For arctan. If we ask you to find the Taylor coefficients, you have to tell us what happens when, some of them are 0. And so this is for all k, for arctan. So kth Taylor coefficients for arctan. Right. Let's see. Shall I do more of this? Yeah, let me do, he has an example in the book, and I don't like the proof of him. So let me give you another proof. We're doing pathological problems for the Taylor polynomial. That's what we're doing here. So here's another problematic Taylor polynomial. Again, let f equal the following function minus exponential to the minus x squared. The picture is it's like this. So this is that guy. I want to show that Pn of f at 0 is not equal at all for all n, which is kind of crazy. That the approximation is just terrible. Fine. So let's find this polynomial. Let's find the kth Taylor coefficient. So we have fk at 0, k factorial. Okay, let's start. We'll do this by induction. So in the book, they complicate this proof a little bit. So let me do it another way. So what was it? We claim that the kth derivative is of the form minus 1 over x squared and the ratio of two polynomials. Where pk, qk are polynomials. We don't really need the degree, we just need them to be polynomials. You'll see why. By L'Hopital, it's irrelevant. Okay, so this is by induction. So for k equals 0, indeed, we have that. So that's the base case. Induction hypothesis, assume, f of k minus 1 is of that form. And now take derivative. So we take derivative of the k minus 1 guy by product rule. This guy becomes, what is it? 1 over x cubed times 2. Pk minus 1, qk minus 1. Plus I'll write it, it's fine. So you have qk minus 1x squared, and pk minus 1 prime minus pk minus 1 qk minus 1 prime. All right. We take out the factor, and we're left with what is it? Qk minus 1, pk minus 1 plus p prime divided by qk minus 1 squared. Okay? So let the top guy be pk and let the bottom guy be qk. Is that okay? So that's the trick. All right. Now what happens as x goes to 0? We want 0 because we want to find the coefficient, the Taylor coefficient. So this guy is the limit as x goes to 0 of this polynomial, of this ratio and the exponential. All right. Step 1, we do a change of variables. So this guy now goes to infinity. All right. And fine. Right. But polynomial. So let me make one little correction. So you have to bring in x cubed. Anyhow, this is not very relevant. But polynomial grows slower than exponential. So we get that, and there's a minus, right? So we get we get 0. So this guy defeats, this is the polynomial, this is the exponential, and it defeats it. E to the minus square goes to 0 in the limit. All right. So we showed something very surprising. We show that Pn at 0 of e to the minus 1 over x squared for k 0 to n is it's 0. So the polynomial is 0. But but e to the minus 1 over x squared is definitely not 0 for x positive. So you go really close, you hit 0, and then you're up again. Okay, now what's the issue with this? Well, that means that the radius of convergence for this Taylor series, for let me write everything in detail. For this Taylor series of e to the minus 1 over x squared is 0. So it's useless. We cannot use it even for x very small. So people have moved on. So I mean, they haven't moved on, but they've developed other tools. And let me see if there's any questions. Is that okay with Taylor series? If there's nothing else, I can move on. Three people. All right, so we move on. So we need better tools. So we move on to the next topic. This is same chapter. This is Weierstrass theorem. So approximation by polynomials. All right. So, okay. Okay. So Taylor series failed. So the Taylor polynomial can fail to give an approximation. So a workaround is to allow the polynomial coefficients to vary, to vary as you take limit. What do we mean by that? So I should do some non-linear example. Well, let's do again this e to the minus minus 1 over x squared. So this guy is continuous. And we'll get the following. We will construct, let me say it differently. For every epsilon positive, let me write here. We will construct a sequence of polynomials Pn of x summation from k equal to 0 to some degree depending on n, and then coefficients that depend on k and n, such that for every epsilon there exists n epsilon, so that in the supernorm for x in some compact set, you will have Pn of x minus e to the minus 1 over x squared would be less than epsilon for all n bigger than n epsilon. So in Taylor series, AKN is equal to AK for all n, right? But here we allow, we can have, and we'll do some examples. AKN not equal to AKN n plus 1. So let me try to draw a picture for this guy. So you have this, And then, so we will have approximations, one approximation. This is like Pn. Then you get a sharper one, Pn plus 1, and then so on and so forth. But Pn has nothing to do with Pn plus 1. These are different polynomials. So you lost the freedom of coefficients, but you gained a better approximation. So anyhow, so let's start building these approximations. Okay. Definition. For f in continuous function in CAB, let Pn of f of x be the following sampling function. So you sample it. Okay, let me do a 0, 1 like they do. So yeah, you sample the function at points, spread out points k over n, and then you put the following weight. That they denote, what's the notation? P, I don't like that notation. It will confuse you with, can I write this something else? Let me call it RKN. In the book, they call it Pn of Kx. So let's see. All right, so what is this function? This is a polynomial. It's called the bursting polynomial. Okay, and what does it do? So let's draw some more pictures. You have your function. Let me just do, let me work with f of x equal x, just to keep it simple. So you have kn gets mapped to, let me change it a little bit. Gets mapped to kn2, 1 gets mapped to a half. Fine, so we have all these guys. And yeah. And you sample the function at these points. So this is the fkn over n. So you have f of kn times nk x to the k 1 minus x n minus k. Okay, so let me justify why they work with this guy. Why is Bn of that form? What's the motivation? The proof will work, but what was the motivation? Let's do this a little bit. Okay, so first we have to look at the building blocks. The function p and kx. So I'm following the notation from the book. Nk x to the k So this function looks something like this. So this is k over n, and at 0 it's 0, at 1 is 0, and it goes up and then down. So let me prove you that this is indeed the picture. Is a bump function around x equal k over n. So let me prove this. So take derivative. We just do product rule. So you have k, xk minus 1. X to the k, and then 1 minus x to the n minus k minus 1 times n minus k. And we set this to 0. Right? That's how you find the max. The binomials get out, and xk minus 1 gets out. So what do we have? We have 0, k, 1 minus x, plus x, n minus k. Right? Okay. So if you solve this, you get k over n. All right. So, and then let's plug in this maximum, and pk at the max what is it? Let's see. Yeah. So n factorial, k factorial, n minus k. So k to the k, and then n to the n, and where else? N minus k to the n minus k. All right. So this is very beautiful, actually. Now, by Stirling's formula, hopefully you can see this by now. This guy becomes n to the n, k to the k, and n minus k to the n minus k. So they all cancel out. This is of order 1 as k and n go to as they go to infinity. Okay, so what's the point of all this? What are we trying to do here? So the picture is you have this bump function, and k over n is about 1. All right. But then if you multiply this by f of kn, you push it a little bit higher. Let me make it more pronounced. So this is f of k. We scale the function. Scale. We scale the max. Okay. So yeah. So indeed, you get a good approximation. So now if you have f being something like x, then you get these bump functions. Let me make it a little bit like this. So this is very beautiful, right? We have these 4 polynomials, so P1n, P2n, P3n, and P4n. And they are all very close to, F1n, 2n, 3n. And if you continue this process, you will get a very improved approximation as you sample more and more points. So by sampling more points, the approximation improves. So this is very different from the Taylor approach. In the Taylor approach, you just find derivatives at a certain point. Here, so at Taylor, you only sample at one point. Here we sample from the entire graph. Here we sample from a dense subset. Zero, 1 over n, k over n. 1. All right, is that okay? Okay, fine. Let's go into bursting polynomials. So we'll prove properties of bursting polynomials. I can go slower. So if you have any questions, no? All right. Let's move on. So we have to prove some properties in preparation of the theorem. So let's prove the following. So Bn of f plus g is equal to Bn of f plus Bn of g, so linearity. You have monotonicity, so f of x bigger than g of x implies the same for the bursting polynomial. So monotonicity. What else? Bn of 1 is 1. Bn of x is x. And Bn of x squared, right? Yeah. Is equal to x squared plus a correction. And another way to write this, I will do it later. So in a sense, this is the mean, and this is the second moment from probability. This proof came from the probabilistic world. Okay, so let's prove these things. Yeah, let me add here the following. So k minus nx squared. So we will explain what this is, but we will need it later. All right. Let's prove them. I think linearity is clear. So we have Bn of f plus g x is equal to f of k over n plus gk over n. And then I don't have to keep writing this. And then you have this polynomial. But summation is linear. So that's fine. What else? Monotonicity, right. So let's see. We have Bn of f minus g is equal to the following. Now this guy is positive, and this guy is also positive. So this entire thing is positive. So by linearity, we get Bn of f is bigger than Bn of g. What else? B1 of 1 is easy. So we have, by 1, we mean the constant function 1. So 1 nk. And hopefully you remember this is called the binomial theorem. So by the binomial theorem, we have x plus 1 minus x to the n. So we get 1 to the n, which is 1. If you have questions, just tell me, because I'm going a little bit ahead. So if you want me to go over something, just tell me. I don't want to go too fast. Fine. So then Bn of x is the following guy. Right. So what do we do? Yes. Okay. So yeah, we have this, but by binomial theorem, by the binomial theorem, what do we have? We have that x plus y to the n is equal to that guy, right? So take derivative in x. And that gives you k x to the k minus 1 and then yn minus k. We did this because we want to get this k guy. So if we divide both sides by n, and so how do you say it? Multiply by x times n, then we get what we have above. So this is a Bn of x. Okay, 1 second. So you get this, and finally set y to be 1 minus x. So you get Bn of x. Okay. I might have to finish early because we're going too fast. I don't want to do too much material. Okay, so now we prove Bnx squared is that guy. Let's prove that. So what is this? This is k squared n squared minus k. So again, we take derivative but twice. We take twice derivative in binomial. So let's see. So this is binomial. And take derivative twice. So let me just write the formula. If you take derivative twice, you get n minus 1. And then as expected, you get k minus 1. And then this guy. So you're almost there, right? You have your k squared a little bit, and then you need this to make it into k. So yeah, first things first, we multiply by x squared over I don't know, over n squared, yeah. So n minus 1, and also set y to be 1 minus x. So we get this. N minus k. All right, and then finally, we have to rewrite this. So first guy becomes bnx squared, and you have a minus guy, which if you do it, you'll see it's bnx. But we already found this. So indeed, bnx squared is equal to x over n. So this is x squared, x minus x squared. Right. We're done for the day. Is this material too easy? Am I going too slow? Because I don't. I don't know. Nobody asks questions. It's like I don't understand. Maybe it's too easy. But you say no. So I don't know. I can go over things, so let me go over it again. Some stuff. I don't know. can I go something over again? Can you tell me something, some part to repeat? Well, tell me some part to repeat, so you can find questions to ask. I mean, there's no point of me going and everybody is lost. No, let's do, can we do this week first? And then definitely I want to talk about it, definitely, yeah. But for a second, let's try to do a little bit for today. But yeah, we will do it today as well for last week. But first, what about for today? Is it all okay? I mean, can I repeat some part? Yes, good, thank you. All right, so, right, where are we? Here. Well, instead of doing the x squared, let me go over again the linear part because the proof is the same and it's a little bit shorter. So here we want to show that Pn of x is x. And the trick is to use the binomial theorem. So here we fix y, but we vary x. And I think it's clear, right? That if you take derivative of both sides, so both sides derivative. So let me do it on the side. So d dx of x plus y to the n, and then d dx of nk, xk, minus xk. Sorry, y. This guy is clear, right? So you get n x plus y to the n minus 1. And you bring in the derivative. Yeah, and that's how you get this. Now, for bx squared, you take derivative again. So n x plus y what is it? Summation nk minus 1. So yeah, you take derivative again for the other guy. So you get n minus 1. And you bring it in. So that's how we got the derivative. So is the derivative okay, or at least are we good up to the derivative? Yang? Okay. Yeah, I didn't think the derivative was a problem. Okay, so where are we? Yeah, I'm doing the simple case first. So we took derivative, then we multiplied by this so that this becomes b and x. There's a question? Okay, yeah, let's see. I mean, where are we? Yeah, so we took two derivatives, that was fine. Then we multiplied by this. And why do we do this? We do it because we want to get this guy here. So let's recall what it was. So let me do the algebra a little bit slower. So this is k squared over n squared, xk, 1 minus x, n minus k, minus, 1 over n, nk, k over n, x to the k, n minus k. Now what, so that's what we get. But what is this guy? This guy is a bnx squared. And what is this guy? This is bnx. Is that okay? Okay, so that's how we got these two guys. And then, we just rearranged. So we brought this to the other side. We use that bn of x is x. So, yeah. Yeah, exactly. Yes, perfect. Exactly. Yes, you got it. When you say the polynomial part was a weight, yeah, thank you, He Young. Yeah, thank you, He Young. That's a very good question. So what I had in mind, because I do a little bit of probability. Where should I go? I should go here. Yeah. So I don't know if you you know a little bit, but let me do a little bit of a sketch of linear regression. It's not part of the course. Just what the motivation is for all this stuff. So given a collection of points, given a graph, a collection of data points, so this is our f. So you have some, let's say it's something like this. Then in regression, we try to find the best linear fit, the best linear approximation, right? So that's what we do. So we have, some weights, A0, A1, and X. These are the weights, the coefficients. But of course, as this graph shows, most data is nonlinear. So in our case, the regression is the following. So we have to do everything. Let me do it carefully. So 0 nx times some coefficient, A1 P0 nx, so on, an p n nx, right? So this is our regression, and we pick the weight depending on the data set. Right? So in Bernstein, we make a concrete choice. We choose, AKN to be FKN. So really what's happening at the back is a statistical problem. We're trying to find coefficients that will maximize the fit. That will maximize the, so you have your your f, and then you have these polynomials. Their summation approximating. So this is the regression fitting the data. Is that okay, Hee-Young? I know we went a bit off, but that's really how it came about, the motivation. This is okay. It's a probabilistic proof. If there are any statisticians, I would love to hear your feedback on this. Sure. Yeah. So let's see. Here. Yeah. Okay. So right. So we found a Taylor series, right? We found this Taylor series, and I mean, now that I think about it, I should not have used the word radius because it's confusing. This is a bad. Yeah, I should have said something else. I guess I want to say the radius of convergence to f of x. That's what we're trying to say. That you know, this limit of this guys goes to e to the minus 1 over x squared. So it doesn't go for all x not 0. It only goes to it only when x is 0, in which case you get 0, which is 0. So all we're trying to say is that the Taylor series fails. The Taylor series fails to approximate this peculiar function for all x not 0, which is terrible. So it only works at 0. Everywhere else, it's a terrible approximation. So that's what we mean, like it has 0 radius of approximating. So only at 0 do we have the approximation. Is that okay, Bin Yao? Yeah, tell me about your last week question. Sure, yeah. I can even find it. Let me see. Yeah, so I'm here. What do you want to talk about? Yes. What is that for? So well, what a good place to continue the proof. So let me try to recall it. Let's finish it because it was only a few lines anyhow. So let's finish the proof. Okay. So let me see if I remember. Yeah. Okay. Okay. So let's continue. So what was it? We wanted to show. Yeah. So what we did was we built a subsequence G and K of X, and it was built out of things that approximate this dense subset. So it was what was it? We said it was K of X. I guess let me write AK in lambda K, the kth coefficient. So it's the diagonal. All right. Anyhow, let me do the proof. So we need to show that G and K is Cauchy in the supernorm. Then we're done. All right. So let me see. What do we have? So yeah, we do a triangle argument. Notation is kind of messy, but we have to do it. Okay, so we have G and K of X minus G and M of X. Now, why do we need the dense subset? Well, since xi are dense, x is inside one of these balls for some I in 1 to n, right? So let me draw the picture. You have your set and you have x, and it falls in one of these xi balls. Yeah, we pick the delta so that x minus y less than delta implies that the whole family is less than epsilon. That's because you had equicontinuity. Now, returning to this, we do triangle for this xi. So g and x k, g and k xi. And then gn of m. Sorry. And then one more, gn of mxi minus gn of mx. So these two guys are fine by equicontinuity. Sorry, I mean the middle guy is fine. What am I talking about? These two guys are fine by equicontinuity. So you get epsilon over 3 and epsilon over 3. And finally, this guy is how we built the sequence. We built G and K, so that G and K xi goes to Li. So again, we get for all nk, nm bigger than n. What's that for? Is xn a convergent sequence to x? No. I mean, try to remember the proof. So what was the proof, right? Where is it? It's a big proof. Yeah, so since K is compact, we took this epsilon dense set. This has nothing to do with X. X is an element of the set, but these are fixed radii. So again, let me draw the picture. So you're given some set, and you want to have epsilon approximation. So you want everything to be in delta balls. So you cover the entire thing by delta balls. And all these guys, they have centers, x1, x2, x3. And that's what we mean. But they cover, K is inside, this union of them. So, so for all x in K, x falls in one of them, like B delta xm. Of the balls, yeah, exactly. They form a finite cover, and so they fall in. So x falls in one of these guys for some m. That's all we're using. Yeah. Yeah, you can. Oh yeah, okay. Yeah, if you guys want to use the mic, you can just do it. You don't have to ask me. Feel free. I know it's hard to type math, so you can.
Oh, okay. So,
Yeah.
Thomas, for the 3 epsilon over 3 part,
Yeah,
what's the middle part? Why the middle part is bounded by epsilon over 3?
that was the diagonalization. Like we built this sequence so that the for every xi they have a limit Li.
So, for both nk and nm, all of the 2g nk nm goes to the limit Li, right?
Yes. Oh, thank you. Yes, exactly. So this is nmxi. Yes. Exactly.
Okay. Yeah, now I understand. Thank you so much.
Sangu, can you also use the mic? It's kind of easy if you like, but okay. So I have a simple question from last week. How did you get this x0 plus 1? Let me see. Psi is within. Yeah, I know. So just take psi. What is it? Take psi is within this interval, x and x naught. So take the delta that bounds their difference to be less than 1, and so psi is within that neighborhood. No, you can do it either way. I know, but like, how do you say it? it doesn't have to be yeah, either way is fine. All I'm saying is, you know, you just need their distance. Just, yeah, let's take it smaller. Um, we just take their distance to be less than 1. Yeah, exactly. Yeah, exactly.